Hi there, in this video I'm going to show you how we can code the Euler method to solve an initial value problem using MATLAB. So what I'm going to first do is define a function, and this function is going to output values of t and y, so this is the independent variable and the function y, and I'm simply going to call this Euler. And the inputs of the function are going to be f, t-span, which defines where we're starting our values of t and where we're ending our values of t, the initial solution y0, and the step length h. Okay, so we remember to end the function, so functions in MATLAB should have beginning, which is the function keyword, and end. Okay, so within the function, I'm first going to define a variable called end steps, and this is going to be equal to floor, and I'll explain what that is in a minute. T-span 2 minus T-span, oops, let's spell it right, 1 divided by h. Okay, so what we've done here is we've calculated the difference between the the end value of t and the start value of t, divided by the step length h, and the floor function rounds this down to the integer below because we need this end steps to be an integer. Okay, now what I'm going to do is define two arrays or zeros, and these are going to be end steps plus 1 number of rows and 1 column. Okay, so this is n steps plus 1 because we got the number of steps plus the initial known solution. And I'm going to do something similar for y. So exactly the same for y. And what we're then going to do is we're going to assign the first value of t and y to be the initial value. So t-span 1 is the starting value of t, and y0 is the starting value of y. So now we need to step through the steps, so to speak. So I'm going to use a for loop to do this, and for n is 1 to the, I'm going to use n steps actually. So 1 to n steps, okay, and the Euler method is quite simple. It's just the nth plus 1 value of y is equal to the nth value of y plus the step length h times a function. This is whatever sort of this function is here, and this will be the ODE we're solving, tn yn. Okay, and we also need to update the values of t, which is the nth plus 1 value of t is just tn plus h. Okay, and then I end that for loop. So this is the function that will use the Euler methods for solving an initial value problem, and what I'm going to do now is I'm going to use this to solve a simple initial value example from the lecture notes. Now with MATLAB, functions need to come at the bottom of any script file, so what I'm going to do is I'm just going to move that down, and up here is where I'm going to define the ODE function and the ODE initial values. Okay, so the function for the ODE, now you can do this in two ways. This is a relatively simple example I'm going to use. I'm going to use an autonomous or inline function. So the function is called f at ty, so this just defines what the inputs to the function f are, and our ODE is quite simple, it's just t times y. So that's defining, just put a comment in there, so that's define the ODE function. Okay, now we need to define the initial value problem parameters. So we're going to use a t-span, so we're going to integrate from 0 to 1. The initial value is going to be 1, and the step length is going to be 0.2. So this is from, if you wonder where these come from, I'm basing this on an example in the lecture notes. Okay, so now we need to solve the IVP, and we're going to use the Euler method. So the outputs are t and y. Essentially, I'm going to copy out this bit here. So Euler, our function's f, we've already defined t-span, we've defined y0, and we've also defined h. At this point, I'm going to run the code just to ensure that there's no errors. It's asking me to save it. Yeah, I don't really care what it's going to be, but you should really save this as something, a meaningful file name. Okay, so it's run. If I just show you, you can see it's run, but nothing's been outputted. Okay, so we can fix that. So we've run, it's run without any problems, but we don't have any output. Okay, so the next thing I'm going to do is I'm going to output a table of results. You don't have to do this, especially for when you know your t and y arrays might be quite large, but for simple arrays like we have here, we can output a table of results, and I'm just going to output a very simple 2-column table, t against y. Okay, so I've used the fprintf statement here. So if I run this and then I show you the output, you can see we have t and y as our column headings. Okay, so I'm going to step through the solution. So this is going to be length of whatever our t is. Okay, and I'm going to use fprintf statements just to output that. Okay, so in MATLAB, we have percent. I'm going to use 2 decimal places, so 4.2. F means we've got a float being outputted, uses 4 character spaces, and 2 are after the decimal point. Okay, and I'm going to do similar for the y value. I'm just going to use 9.6f. Okay, and then I'm going to use a carriage return, which is \n. So let's see what that gives us. Oh, I think it won't give us anything because I haven't actually told it what the value of f and n are. So to do that, I put t and n. So we have tn and yn. Let's see what that gives us. Yeah, you can see we have a table. It's a bit garbled. I forgot to put a carriage return after that, after our headings. So that goes here. So you don't always get it right first time when you're coding. Okay, so I've made that change, and you can see we're presented with our solution. Okay, quite often the best way to present a solution is to plot. And fortunately, in MATLAB, plotting is quite easy. It's simply the plot command, and I'm going to plot t against y, and I'm going to use a blue line with circle markers to do that. Okay, so and let's put in a couple of labels. So x label, let's say we got our horizontal label is going to be t, and I've used LaTeX syntax here, so I just need to tell it, but I'm going to use the LaTeX interpreter. You can see it's come up as one of the options, and do similar for the vertical axis, which is going to be yt, and again interpreter. I'm going to use LaTeX. You don't have to use LaTeX. I just find sometimes it helps, especially if you've got equations in your labels. And let's see what that gives us. So if I run, we've got a couple of problems with the labels, but you can see it's given us a solution here. What I am going to do is just to tidy this up a bit. I've got a mistake in the axis labels, and they look a bit small to me. So what I'm going to just do is fix that, and I can increase the font size by, let's say, to 16. And let's see what change that does. If it's just hidden underneath, you can see they're slightly bigger. Also, what I don't, it's just a personal preference. I don't tend to like it when your part of your plot is very close to the edge. So I like to use padded axes, and to do that, you just do axes padded. If we run that one last time, you can see we've got our nice solution plot.